Hello, everyone. Thank you all for attending our presentation. Event-based fuzzing, cache-based research, and commonplace finding bug through a bug. It's a great pleasure to participate in Black Hat Europe, and we are sorry that we couldn't be there. We are currently in Chengdu, China. Hope you have a good time. I'm Yang Huinian. Today, I will be co-presenting with my colleague, Qingyu. Firstly, a brief introduction. I'm a security researcher in Oppo Amber Security Lab. My job is to take care of security of Oppo products, mainly about OS, and I also spend some time on Chrome and Android security. And so my briefing today will involve both of them. Now I will let Qingyu to introduce himself.
Hi everyone, I'm Qingyu. I'm a security researcher in Oppo Amber Security Lab. I mainly focus on vulnerability discovery, exploitation, and the defense of the Android Linux kernel.
Okay, our briefing today is about finding more bugs with one bug from some other perspective. We have learned from studies and presentations of many excellent security researchers on how to find vulnerability through the attack surface analysis and module analysis, which is very effective. But to find the potential value of a vulnerability as a way to find more, we've summarized 4 key strategies. These 4 key strategies we're going to share today includes 1 enlightening fast solution and 3 audit experience. And through these models, we have found over 40 vulnerabilities in Chrome and Android vendors. So, agenda for today. We will start with a story, the beginning of the journey, 3 identical CVEs. And then we will show 4 effective and intriguing bug hunting approaches, and finally come to a conclusion that will hope will be enlightening. The left part here is a familiar page. Chrome security bugs are publicly disclosed by Google after fixing, which have great learning value. It was April 2020 when I first decided to look for vulnerabilities in Chrome. So I started looking for inspiration from here. The $20,000 report on the right caught my eye immediately, and I decided to take a look at it right away. CVE 2019-13699, founded by researcher Mo, may allow sample escape from a compromised renderer. Looking at the proof of concept, it appears to be a targeted file sample for the media module interface, but the vulnerability does not occur in the media module interface. This is triggered from the desktop capture module interface, but the use after free actually happens in desktop capture. The screen capture notification UI views is raised by the blink module media stream type of display video capture. I won't go into detail about how the vulnerability works. We just need to get a concept in our heads that the vulnerability starts from the desktop capture module interface and goes to the screen capture notification UI views. And so I verified the proof of concept in the latest version. And yes, it seems to be fixed nicely. But with my curious strolling clicks, it crashed. What happened? I first thought there was some problem with the patch. And I looked at some more information here, and it looks like another problem. Well, I thought, it's been public for over 3 months, and no one has ever done anything like this. For that, I got a lucky $15,000 for CVE 2020-6466, a really fantastic start to the Chrome bug hunting journey. And after a brief analysis, it seems that some user clicks enable this code to go deeper, from the notification UI to tab sharing, unlike some module interface bugs, which may have been discovered and fixed by Fuzzing before the early release. Now, has the story ended? Not really. After a period of time, researcher Kahalis Harni found CVE 2020-16001 based on CVE 2020-6466, which also shared the exact same proof of concept, which means that these 3 CVEs were triggered by the same proof of concept, except for their user action. We have already learned many fuzzers that are good at generating rich code to trigger deeper logic. Now, can we conclude that user action can increase code coverage and constantly serve as a fast input? Let's verify it in the extension fuzz of Chrome. So the first model is about adding different events to the fuzz, the important experience we just got with user actions. Now, a little background for extensions. Extensions are small software programs that customize the browsing experience. They let users telephone functionally and behavior in many ways. There are thousands of different examples of published extensions in Chrome Web Store. For me personally, I find that the dark background and page translation very convenient and useful. Extensions let you extend the browser by using APIs to modify browser behavior and access web content, like activating tabs, modifying net requests, and so on. For example, using the Chrome Bookmark API to create, organize, and otherwise manipulate bookmarks. And to create an extension, you assemble some resource, a manifest, JavaScript, HTML files, images, and others. So the obvious way to start a fuzz is to generate these valid content files. So I used Tomato to generate the API calls as shown, which worked well in the beginning. And there are soon 2 CVE founded. And as you can see, this 2 proof of concept is relatively simple as are the grammar rules. Now the normal next step would be parallel fuzzing, exploring communication events and race condition possibilities. For that, we've got CVE 2021 to 30614 triggered by 2 extensions, and CVE 2021 to 1143, a race condition bug. What's next? Then I thought of the story at the beginning. I mean, the extension can also invoke many user interface, such as tabs and windows and bookmarks that a user can manipulate. And the advantage of this is that it can trigger event callback functions of user interface, not just extension event callback. Of course, I can't have manual clicks at random, which is neither realistic nor difficult to reproduce. So what I need is a constant flow of events and reliability of reproduction. So I use some tools that simulate their user actions. Puppeteer here is a Node.js library which provides a high-level API to control Chrome over the dev2 protocol. Puppeteer can run in both headless and non-headless mode, and it supports extension interaction. It supports some powerful features like automated form submission, UI testing, keyboard input, but for my purpose, it has some limitation. Basically, the scope is limited to browser context. And the Xdo tool here is a system level tool, which an unlimited scope, which is more ideal for interacting with files outside of page or just any other software. It is quite easy to use as well. These are some cool tricks that are very useful for browser manipulation. This is clicking, closing, resetting browse, dragging. I found many vulnerabilities triggered by drag events in recent times, and this is how bring up Chrome and visit and access Black Hat root. Regarding the real example, the accidentally discovered vulnerability mentioned at the beginning of the presentation can be triggered by such an automated script, which is simple and effective. So we add Xdo2 to fuzz, and with the help of Xdo2, we found these interesting vulnerabilities. CVE 2020-6554 requires the user to close tab windows, which is actually a special situation here where the vulnerability occurs at the stage after the browser receives a closed event. And this duplicated issue requires the user to close tab very quickly. And if you are not fast enough, it will not trigger. This is one of the reasons we strongly recommend using a simulated approach. CVE 2021-21214, and unspecified environment variable, network state related. Here we'd like to share some tips for the user interaction in Fuzz. The first point is that the focal point can be anywhere. For a page that lacks a valid component, more than 90% of the space is useless space. For this matter, we can use a weighting approach or optimization. For example, weighting the effective area, the top part of the browser, and also the constant position of the area can be set separately. The second point is the blacklist area is necessary. You certainly do not want an accident of random shutdown or change of strange system settings. The third point is that some code is executed only when the browser is closed. And if something goes wrong in this part, the fuzzy parent, the normal fuzzy parent process can't catch it, but it can be captured by user clicking close. This is an extra benefit. I have also noticed in recent times that more and more similar vulnerabilities triggered by user actions are founded, and most of them are relatively dangerous. You can search by this attachment:webm, while most of them are in WebM format, but of course there are some other video formats. And there are a large number of user interaction events on cell phones, some of which are well known, such as Bluetooth connection and disconnection, and the reason pixel screen lock bypass vulnerability. And there are others like the USB WAN confliction here to be further explored. Now, here is a quick recap of these main points of this section. Firstly, delving into valuable bugs can be unexpectedly rewarding and enlightening. Secondly, focusing on event handling logic, user actions, etc., can increase the coverage of code execution and therefore serve as a kind of other input. Now, in this section, we will touch on some experience we've gleaned from the patch-based research and then show 2 examples as illustrations. First, for a moment, recall how you might feel when you see a check code or a monthly security bulletin. Do you feel pity because another vulnerability is missing, or feeling frustrated? Bug hunting has become more difficult. While on the other side, it can be different. You may be wondering if this patch is perfect. Sometimes you might be inspired by a particular detail. Hopefully, you'll be excited, because this means the execution flow here can go deeper. Our first case, CVE 2020-6509, is an interesting bypassing example. As a browser process used after free, this is a potential sample escape, but as it requires the user to install an extension, this is mitigated down to high severity. The fixed opener function of tab strip model is called when the tab is being detached or moved. As its name, fixed openers, it is called to ensure that no web content data has its opener set to the web content at a given index. It does this by setting the opener of any tabs that reference the tab at index to that tab's opener. And from a security point of view, if such a tab which is its own opener, is removed, the same fixed opener logic will cause the opener of any tabs referencing it to point to a dangling pointer, so that we can lead to use after free errors. So we first try to appoint a tab's opener as the tab itself. Things are not so easy, and we get this error, which is a obvious forbidden. What about updates? This seems like unfeasible either. Fortunately, however, there are more than just 2 pieces of code that can set this property. As you can see, through tabs move function, the index of the tabs will be updated, and this is purely position related. So if we construct two tabs, make them opener for each other, and then swap their positions, we can finally get the opener point to their own, and therefore trigger this vulnerability. And our second case is about going deeper. Let's see CVE 2022-32625. In this multi-layer auth, which is very common in modules like GPU, a newly patched is on first loop. However, the second loop check is not so sufficient as the first one, which can cause out of bounds read. And these are some of the vulnerabilities we found through timing follow-up of patches. And from the distribution here, it is reasonable to assume that patches for modules with more complexity are worthy of deeper investigation. Now, brief summary for this section. Incomplete or insufficient checks happen from time to time. As for effective fix, try other way to bypass or go deeper into the subsequent logic, which is more feasible for more complex modules. Now, I would like to pass it over to Qingyu, who's going to talk to you about another interesting strategy.
In this section, we will summarize our experience in real world, discuss some real-world scenarios that can create vulnerabilities. As we all know, the Android ecosystem contains a large number of terminal products, including various phantom vendors and various components and application providers. And in the security scenarios of these real products, there are more diverse situations. For a simple example, the GKI is after version 5.4 of the Android common kernel to make the kernel more consistent and secure. Then vendors add their drivers code. Then OEM add their features code. From here, we can already see that the branches are increasing, and that Android is not only the kernel code, but also a lot of native and framework code. From the Android monthly security bulletin, we can see some of the main vendor figure. And now, vendors will add their drivers code to support their own hardware and chip, and then supply it to different OEM. Note that each vendor will create a different mainline branch because of the different specification of the hardware platform. For different products, different targeting and diversity, OEM choose different models of hardware and inherit different branches in order to adapt to different product features. Each product will merge different code. Therefore, the kernel branch is further increased. Besides hardware, OEM will also develop their own special features in the software. For example, now many cell phones focus on camera as a selling point. This will lead to different camera, video, and multimedia library, as well as inherit its upstream vulnerability. Some inherit on a branch's commit of an open source lab, then develops their own feature. This awkward situation would create new vulnerabilities. The above is just an abstraction of some gap situations. Perhaps this is a reality. 4-dimensional coordinates because each sub-repository under the repo project may also be in different timeline. These situations are due to the actual needs scenario of each product, which brings some security risk, which create a lot of opportunities of finding vulnerability. The important thing we want to talk about is the direct impact of the upstream and downstream relationships. In fact, the upstream Linux kernel also has its own upstream submodules, such as net, ARM, FS. A few years ago, when CVE 2017-8890, a high-risk vulnerability from the upstream Linux kernel appeared. We rooted Android phones that had not yet been patched. And a year later, We surprised to find that the POC still worked on the then latest CentOS distribution. Then we exploited it. This is a powerful example. The upstream Linux kernel generic module vulnerability affects almost all Android devices, and is also fixed and public earlier than Android, which is equivalent to a downgrade attack for the downstream without rewriting the firmware. This year, I found CVE 2022-24022 using a simple file read-write fast tool. Then I found out that a few months ago, it seems to have been a patch in the upstream Linux kernel. This can be a glimpse of the impact of the upstream too. In my first year of learning security, I learned that Linux is based on the file system, so I have an idea of random read-write tool to test all file nodes. Although I thought, how can Linux have such a simple read-write vulnerability? Until this year, I put this little fuzz on different devices. After a period of time, I got at least 50 crashes and over 5 CVE from them. These problems are most similar. I think this is mainly due to the complex branches in the Android ecosystem. In those of similar functions, it is easy to have similar vulnerabilities. Perhaps developers prone to make similar mistakes. First, we look at the dirty pipe famous this year. It looks very similar with the previous pipe-rat patch. The first pipe-rat patch was added in 2013, and then the dirty pipe appears to repeat the same error this year. We can use a simple vaguely statement on the rat to scan the dirty pipe's two functions that were not fixed before. We can analyze the patch and summarize the vulnerability model, and then use the CodeQL or Waggly to find these problems. Waggly is a static code scanning tool developed by Google Project Zero, very convenient and efficient. We have used Waggly to summarize some vulnerability models and submit some security issues. Compared to the Android common kernel, there are more multi-branch and multi-version problems in the vendor and OEM's code. This is a vulnerability in the USB Type-C driver. We found this 1-byte OOB write problem on a model with the help of KSM. Then we found a second similar problem in another model by using the CodeQL on the right. And this is the camera driver problem. We first found this integer overflow problem in the fuzz of a module, and then found several similar vulnerabilities in different modules with similar functionality by using the CodeQL on the right. These are some vulnerabilities we found by one vulnerability in a complex scenario perspective. My friend's grandmother said to me, when you see one bug, you already have 1,000 bugs in your home, so we have to find more bugs through one bug. Sometimes we trust the previous one. We trust the upstream and the suppliers. We trust that the code function will return right, so the vulnerability appears. For the midstream and downstream kernels, if a vulnerability is missed, it may not be fixed until the next major kernel version upgrade. One vulnerability is enough for a attacker. So for the main OEM, which have a large number of users, it is necessary to find efficient ways to solve the vulnerabilities under the upstream and downstream and multi-version branches. We also found that the higher the convergence of the model, the more accurate the scan result will be, and the lower the false positive rate. The higher the fastness, the more result we get, but the false positive rate will be higher. In the same module, using a model with higher convergence will give better results. Next would be a relaxed session. There are also cases of commonplace in the code, where keywords include should, error, etc., but the actual check and return are missing. Next, we will discuss a few interesting examples. Although this case may not cause a crash, but will cause a logic error. First, take a look at this code. Very perfect comment. This comment does almost everything, which perfectly explains the structure of REQ and RESP and the sets of each member. You can see that every is 16 bytes. However, in the later code directly ignore it. OOB read in the structure is sometimes not checked by ASIN. If you are interested, you can search what types of vulnerability ASIN cannot detect. So this comment can be a big help to us. We summarize such cases as check-in comments, and the code here on the right can help us. Then look at this function. It successfully does the check and print the error log E, but unfortunately, there is no return. The wrong data will continue to fly in the code and generate the error later. We summarize this kind of situation as check and run without return. The code here on the right can help us to find some of these problems. In this code, inquiry name is passed in and then assigned to a global variable. Then check its size. At the point, the wrong value has been written to the global variable. We summarize such case as check after use. So the code here on the right can help us to find some of these problems. In the red box in the code below, both REQ and the image says REQ accept the return value of a function, but are passed to the next step without checking, and then cause an error later. We summarize such case as return without check, and the code here on the right can help us to find some of those problems. This is a problem that Qualcomm has fixed. I think this problem is a function does not use the parameters passed in by user. Through the red program, we found over 10 similar problems. And here are some of problems we found with these models. We can use CodeQL or Wegley to help us scan for such problems. And different models are suitable for different cores. Unlike other vulnerabilities we discussed earlier, which are coded, this type of error is more common, and we hope to reduce the attack surface by these situations we have seen. And finally, come to the conclusion. There are basically some ideas we shared today. 1. Sometimes unexpected funding can inspire new approaches, and event-based fuzzing improvement can help identify security problems in complex systems. 2. Fixed does not mean completely secure. You can try bypassing or going deeper. 3. Using CodeQL or Wegley could be a better solution to realistic code scenarios, makes bug hunting for customized products more efficient. And we'd like to thank all the vendors for working diligently with us to remediate the security vulnerabilities. We thank you guys so much for your time today and hope you pick up a couple things.